We're always told the solutions to the climate crisis are going to be super complex, really high tech. But what if one of the most powerful answers is actually ancient, simple, and sitting right under our feet? In this explainer, we're going to dig into the surprising story of how we can literally bury our carbon problem for good.
Okay, so here's a number that keeps climate scientists up at night. 1,500 parts per million. Some of the worst-case projections show that without some pretty drastic action, atmospheric CO2 could hit this level by the end of the century. Now, to put that in perspective for you, we're at about 420 ppm right now. A jump like that would change, well, pretty much everything about our planet.
So that's the big question, isn't it? For centuries, we've been pulling carbon out of the ground. But what if we could actually reverse the flow? What if we could take that carbon right out of the atmosphere and lock it away, safely, in the soil?
Right, so first, let's just quickly frame the core challenge. For over a century, our industries, our daily lives have been pulling ancient carbon out of the ground and just pumping it into the atmosphere. The fundamental problem, as our source material lays out, is that this whole system is dangerously out of balance.
And this brings us to our kind of unlikely hero, biochar. I mean, it just looks like simple charcoal, but it holds a remarkable power, the ability to grab carbon and lock it away for a very, very long time.
So what is this stuff, exactly? Well, biochar is made through a process called pyrolysis. The easiest way to think about it is like baking, but without any oxygen. You take organic material, stuff like wood chips or leftover crop waste, and you heat it to really high temperatures. This completely transforms the unstable carbon in the plant into a super stable, really dense form of carbon.
And when I say stable, I really mean it. Some studies estimate that certain types of biochar can stay in the soil for over 1,000 years. So this isn't just some temporary fix. It's a way of locking carbon away on what's basically a geological timescale.
This slide shows you that chemical transformation in action. See on the far right, you start with regular biomass. That furnace in the middle, that represents the pyrolysis process. And as you follow it to the left, you can see on that chart how the material becomes more aromatic. Now, in chemistry, that just means it forms these incredibly stable ring-like structures. It fundamentally changes the carbon into a form that's way more resistant to breaking down, making it closer to permanent graphite than it is to a decaying leaf.
So here's the crucial point. Why is it so incredibly durable? What's the secret behind its strength? Let's dive into the chemistry for a second.
The secret to biochar's strength is something scientists call fixed carbon. Think of it this way. When you heat that biomass, some parts burn off as gas and vapor, but what's left behind is the non-volatile, rock-solid carbon structure. And that fixed portion is what gives biochar its incredible staying power.
This diagram breaks it down perfectly. You can see that biochar has two main carbon components. There's the orange part, the volatile matter. That's the less stable stuff. And then there's the purple part, the fixed carbon. That's the high stability stuff that we really want. The whole goal of making good biochar is to maximize that purple section.
So how do you do that? Well, it turns out temperature is a huge factor. As this chart shows, if you make biochar from oak wood at 600 degrees Celsius, you get a higher percentage of carbon than if you do it at 400 degrees. That hotter process burns off more of the volatile stuff, leaving behind a more concentrated, more stable carbon product. Simple as that.
Okay, so we know what it is and we know why it's so stable. But how does it actually work once it's in the soil? I mean, what does it do down there to lock all that carbon away?
Well, biochar doesn't have just one trick. It has a whole toolkit of methods for sequestering carbon. It directly adds stable carbon, for sure, but it also acts like a shield for carbon that's already there. It helps build protective soil structures, and it even makes the soil healthier for plants, which in turn pull down more CO2 from the air.
And this diagram just brings it all together. You can see atmospheric carbon up at the top, which biochar helps pull down into the soil in a bunch of different ways. As you see on the left, it directly increases the soil's carbon content. But look closer at its porous structure, shown in the bottom left. It acts like a little safe house, protecting organic matter from the microbes that would normally break it down. It also helps form those little soil clumps, or aggregates, that physically trap and protect even more carbon. It's a multi-pronged attack on atmospheric CO2.
So what does this all add up to? When we look at the big picture, biochar really starts to look like a powerful, scientifically backed tool in our fight against climate change.
And hey, don't just take my word for it. The researchers behind our source material conclude that biochar's potential as a sustainable and long-lasting solution is solid. It's a grounded, effective way to turn our soils into massive carbon sinks.
Which really leaves us with a final, powerful question.
We so often look to the skies, to technology for climate solutions. But maybe the answer has been right here under our feet the whole time. Could the future of our climate truly be buried in our soil?